Thank you for having us. Firstly, Altech Chemicals is an Australian company. We're listed on the Australian Stock Exchange. What I want to do is talk about the future of lithium-ion batteries, because we have been doing a lot of work on our high-purity alumina as an alumina coating for anode materials. As you would have seen in the news, on the Tesla Battery Day last year, Tesla has announced that they want 3 terawatts of factories to be built by 2030. And that's equivalent of 20 gigafactories that needs to be built around the world. And they also announced the use of silicon in their anodes, an increased use of silicon in the anodes. And I'll explain about that in a second. Just a bit of education on lithium-ion battery. You've got a cathode on the right-hand side. You've got an anode on the left-hand side. As you charge the batteries, the lithium ions move from the cathode to the anode. And when you discharge a battery, the lithium ions move back. What a lot of people don't realize, that 10% of the lithium actually stays on the anode side and becomes inactive to the battery. So this is called the first cycle lithium loss capacity. So imagine 10% of the lithium before the customer even gets the battery becomes inactive. And essentially, this has been a problem that has been facing the industry, and people have been trying to resolve this problem. And there's many research that shows that alumina coating works well to prevent this SEI layer from forming. But currently, the alumina coating technology is very expensive and not commercial. So what we have, if we explain what that happens on at a particle level, the lithium forms this SEI layer around the graphite particle, and it becomes inactive to the future performance of the battery. The other thing is that hydrofluoric ions is in the electrolyte, and they break down the SEI layer. So as it breaks down the SEI layer, more lithium is absorbed. So there's a constant degradation of lithium in the performance of the battery. And if you look at a battery curve, this is what the curve looks like. It drops away from 100%, and at the 80% mark, that's the life of the battery. Now, as I mentioned, there's a lot of research and work that's already been done that shows that high purity alumina improves this issue. It improves the first cycle loss, it improves cycling stability, it improves the high rate performance of the battery, it improves the fast charging capability, and it prevents thermal runaway. So this is some of the typical work that's happened. This is a performance of an uncoated graphite material versus a coated graphite material. So as you can see from this graph, after 200 cycles, a coated graphite material with alumina is 85% capacity versus 75% for an uncoated. I did mention about thermal runaway. This is another test that has been done by various groups where they do a nail penetration test. And on the left-hand side, you've got a non-coated graphite. The temperature skyrockets to 600 degrees, and you get virtually the battery catches the light. On the right-hand side is a coated graphite battery, and through the temperature goes up to 90 degrees, and essentially it remains intact. So coated graphite with alumina also helps with safety of the battery. Now, there are 3 various ways of coating graphite, alumina onto graphite: the vapor method, solids, and the liquid method. The vapor method is called atomic layer deposition. It's costly, complex, and is not suited for mass production. We're focused on the liquid method using our technology, and essentially we can coat a graphite particle with a very thin layer of alumina, in fact, around 2 to 3 nanometers. And what it does, it prevents the lithium from forming the SEI layer, and hopefully it allows that lithium to be plays a part in the future performance of the battery. What we find with our alumina coating is that it doesn't stop lithium from going through it. So it doesn't stop the performance of the battery. And what's the more interesting thing is that there's a lot of research that shows that alumina absorbs this corrosive hydrofluoric material that I mentioned before, and it turns it into an inert material. And typical of some of this literature, this is some people that did the work, and they say that the alumina coating scavenges the corrosive hydrofluoric ions. Now, if you look at the coated versus uncoated, that's what we're aiming for. When you have a reduced cycle loss capacity, you have an extension of battery life. This is what we've achieved in the laboratory today in our research and development laboratory. On the left-hand side, you've got a graphite particle with our very thin, continuous alumina coating. And on the right-hand side is typical of what the industry is trying to do, very irregular coatings and very thick coatings of alumina. So we believe that our process is a cheaper process. It's easier and simple to commercialize. Because we're using high purity alumina, there will be less contamination to the battery. And you can see how the coating is very uniform. And because we use very low processing temperatures, our cost difference is significant. So we think this is breakthrough technology, and we think this is a game changer for the lithium-ion battery industry. We have now done the test work in batteries with coated graphite, and we see very encouraging results of coated graphite versus non-coated graphite. So it certainly performs better in the battery. We have recently signed up an MOU with SGL Carbon, one of the largest European graphite producers today, and they're very interested in us coating their graphite with the alumina coating. So we are partnering them as we go through. As I mentioned before about Tesla and the increased use of silicon in the anodes, now silicon is a very promising anode material. The reason is it's got 10 times the capacity compared to graphite. So there are 10 times more active sites that the lithium can sit in. And so it's actually a very promising material. Why isn't it being used in the anode material today? There are three major problems with silicon. The first one is that the expansion is 300% in volume. Number two, the first cycle loss instead of 10% is close to 40 or 50%. And there's also a high fade. So if you look at the graphite versus silicon graphite, you can see the fade drops off very quickly. And you actually have a reduced battery life if you try to use silicon today. I mentioned that the first cycle loss capacity is much higher. It absorbs more lithium in the SEI layer and makes it inactive. So this is the other big problem. And I also mentioned the lithiation, where the volume change is 300%, to the point it actually fractures. Now, when the silicon particle fractures in the anode material, you get delamination, and that's a problem for the battery. So these are the major three problems with silicon material. And there are research that's been done where they've used alumina coating to prevent the fracture for the silicon material. So that's what we're doing. We're using our alumina coating on silicon particles, and we hope that it'll contain the silicon particles and prevent it from fracturing. We have now done the test work in our laboratory. We've successfully coated silicon particles with alumina, and you can see the picture there of how continuous that material is. And our hope is that this is what the end result with. The red line shows a coated silicon graphite composite with extra energy from the silicon particle and increased battery life. Now, how does that transfer to a vehicle? Well, if you look at a Model 3 in a Tesla, it does 423 kilometers. By adding 10% silicon, it goes to 700 kilometers. 20% silicon goes to 1,000 kilometers on one single charge. And at 30% silicon, 1,300 kilometers on a single charge. Now, you can see the dramatic improvement in battery performance just by adding a little bit amount of silicon in there. And obviously for the car manufacturer, they'll keep the range the same, but reduce the cost of the battery. We've also recently signed up a MOU with Ferroglobe, one of the largest silicon producers in Europe. And they're also very interested in our coating of their silicon. And we are very excited to partner with them as well. Now, how do we apply this technology in commercial terms? Well, we have announced a pre-feasibility study for a battery materials coating plant in Saxony in Germany. Now, Saxony is the state where a lot of EV cars of manufacturers have been built and battery plants. And our first phase of this project is for a 10,000 ton per annum graphite coating plant. We have an option to purchase the site. We're right on the border of Saxony and the state of Brandenburg. And essentially the site is on the left-hand side. And recently we acquired a research and development space and some offices on the site. We're very focused on Europe. It's fair to say that the next decade will be in the lithium battery story will be Europe. I guess in the past it's been China, Japan, and Korea. But we believe that in the next decade is going to be a European story. There is 600 gigawatts of battery capacity being announced in Europe by 2024, all driven by regulations. So car manufacturers need to average below 95 grams per kilometer of CO2 emissions. And in order to do that, they have half their fleet has to be EVs. And so you have a lot of car manufacturers, Volkswagen, announcing gigafactories by 2030 to meet that demand. And this is a chart of showing all the announced battery capacity in Europe, some 600 gigawatts of power, companies like Northvolt, FRA, Tesla, LG Chem, and so on. And if you look at the graphite demand from that, something like 600,000 tons of graphite required just from Europe by 2030. And our view is that if we can coat the materials of graphite and silicon, that's our future business. So looking out in the long term, that's our business, coating graphite materials and silicon and putting it together as a anode composite. Just to remind you, we started our journey as a high purity alumina play with a 4,500 tons HPA plant in Johor. As you know, high purity alumina is a feedstock for the LED and lithium battery industry. So exciting growth demand there. The market is expected to grow from 30,000 to 270,000 tons per annum. And we have a 250-year kaolin mine in Australia, where we will ship the kaolin to our proposed processing plant in Johor, a chemical plant where we extract the high purity alumina from kaolin. The process itself is very disruptive. We sit on the lower cost quartile because we don't use aluminium metal as our feedstock, and we have patent protection. Recently, we've been certified as a green process by Cicero out of Norway. And the reason we are a green process, the fact that we don't use aluminium metal, we essentially use 49% less greenhouse gases to make every ton of HPA compared to the current process. We have a 10-year offtake with Mitsubishi, and we have a build by SMS. We're in the stages of funding the project. We have debt from KfW, 119 million of senior debt from KfW IPEX-Bank. We're currently accessing 144 million of secondary debt from the listed green bond process. And we're also looking for joint venture partners for the 100 million for project equity. The project is very cash rich. The NPV for the project is about $500 million US, and the EBITDA is about 76 million. Now, the company has raised close to 50 million in the last 3 years, and essentially we've commenced the construction process, de-risking the project. So by getting on site, getting all your permitting approvals, environmental approvals, we essentially de-risk the project. So we now know the ground conditions, we've leveled the site, we've built retaining walls, fencing, and we built this very large maintenance workshop which we'll use during construction. We've also built underground tanks and also a electrical substation, which is a key part of the process. So essentially, the project will have a running start when finance comes through, and we're looking forward to building this plant. So thank you, Clive.